We're going to look at solving systems of equations by substituting. So using our substitution method. So I just want to review what substitution means. And when we know when we substitute that we are replacing or plugging in. So I want you to think about that as we go through this. As we substitute, we are replacing or plugging in. So let's go ahead and just look at a review question here. It says y plus x times z. And it tells you what the letters are. It tells you x is 9. So we're going to substitute. We're going to plug in the 9 for the x. And we're going to plug in the 11 for the y. And we're going to plug in the 8 for the z. So if we were to substitute and plug these numbers in, we would get 11, because that's what we plug in for the y, plus the x we're going to substitute with 9, and we know x next to z means multiply. So it would be 9 times 8. We need to make sure we use the correct order of operations. So we have 72 plus 11, and we get 83 as our answer. So this is a review actually out of topic 1, where we're looking at substitution and we're just plugging numbers in and evaluating. Okay, that's what we're doing when we're solving these systems of equations. You want to look for when you have a variable with a coefficient of 1 set equal to something. So if we look at example 1, we have a 1y here. What does the 1y equal? It equals 3x. So we can substitute that equation into our other equation. And I'm going to tell you every single time what I suggest you do. I'm going to box this in. I'm going to draw an arrow to what it's going to. Y, we are plugging in 3x into the y value, just like I did before in my review up above. Okay, we are plugging in, we're replacing y with 3x. So let's go ahead and I'm going to write the letter x plus, instead of the letter y in parentheses, we're going to put what we are substituting, which is our 3x, equals negative 32. So I tried to use colors here to help. You can see that our original problem we have all in black, and then what I boxed in blue is what I replaced for the y, and I wrote it in blue. So now it just becomes a problem that we need to solve. 1x plus 3x's is 4x, which equals a negative 32. And 4 times x, the inverse is divide. So we're going to divide both sides, and our value for x is negative 8. Our value of x is negative 8. We know that when we have a systems of equations, we are looking for an x, y value. We're looking for an ordered pair where they cross. And hopefully we remember this or recall this from the first lesson with graphing. So we know our x. Our x is negative 8. What do we have left to find? We have to find the y value. And I always suggest taking one of the original equations. I'm just going to pick this original equation and write it. Y equals 3x. Well, we're going to substitute again. You know what the x value is. You just found it. It's negative 8. So I'm going to plug that in for x. I'm going to bring everything else down. And I know that yellow is hard to see. I won't use that again. I apologize. So we have y equals 3 times negative 8. So we have y equals negative 24. So I want you to think back to the visual. These two equations, if we were to graph them, they are going to cross at the ordered pair negative 8, negative 24. They're going to cross at the ordered pair negative 8, negative 24. That is the solution. If you were to plug those into either one of those original equations, you would get equal, the left side equal to the right. We also know, and we learned in our last lesson, that this is an example of what we call a one solution. One answer. That is the one point they cross at. Let's look at another example. Again, we're trying to identify where our x or our y value has a coefficient of 1. And if I look at these equations, I have negative 2x plus 5y equals 19. No coefficient of 1 there. And I have 3x minus 4 equals y. Equals that 1y. That's what we're looking for. So we know what y is. Y is going to be this 3x minus 4. We're going to circle it or box it in. We're going to plug it into the variable y in the other equation. So as I write this out for you, we have our negative 2x plus, we still have our 5. But instead of writing the letter y, we are going to plug in 3x minus 4. And remember, always substitute using parentheses. And hopefully my colors are helping as well. And equals 19. And so now we are just going to go through the solving process here. I would change, draw my line down my equal sign. I would change all subtraction to add the opposite. Step 3 would be apply the distributive property. So we're reviewing kind of solving equations here. When I apply the distributive property, 5 times 3 is just 15x. Plus 5 times negative 4 is a negative 20. And that equals 19. And don't forget to bring down your negative 2x in front. Now we need to ask ourselves, do I have any like terms? I do. I can combine my negative 2x and my 15x, which gets me 13x plus negative 20 is going to equal 19. We need to isolate the variable and get it by itself. So I'm going to add 20 to both sides. So I have 13x equals 39. 13 times x, that inverse operation would be to divide. Whatever we do to one side, we do to the other. And our x variable here does equal 3. Again, we need to find an xy value. This is only the x value of positive 3. So we need to pick one of our original equations. I'm going to pick the 3x minus 4 equals y equation. We know what x is, so I'm going to plug in for x what we just found, which is 3. You'll notice I'm writing everything else as the original. Why are we doing this? Because we're trying to find the y value. And so when I do the correct order of operations, 3 times 3 is 9, minus 4 is y, well 9 minus 4 is 5. So if you were to graph these, if you want to go back to the visual, these two equations are going to cross at the ordered pair 3, 5. That's where they're going to cross at. That is the solution that will make both of these equations true. Let's look at one last example. Here we have 4y equals x, and we have 3x minus y equals 70. And so hopefully you're identifying where you see the variable with a coefficient of 1. And you actually see it twice here. I see it here, and I also see it here. But we want it just to say like 1x equals or 1y equals. So we're going to take this 1x equals 4y, and we're going to plug this in for the x value. Remember, we're substituting in for what x is. 1x here is 4y's. And if I rewrite it, and I hope the colors help, I'm going to have the number 3. I'm plugging in for the x. I'm plugging in a 4y, because that's what I circled, minus 1y equals 70. So now we've taken our two equations, we've substituted, we've taken one equation and plugged it into the other equation. So we have 3 times 4, which is going to give you a 12y minus a 1y equals a 70. 12y's minus 1y is going to be 11y equals 70. 11 times y, that inverse is to divide. Whatever we divide one side by, we need to divide the other. So we get kind of a yucky fraction here. Y is going to be equal to 70 elevenths. And that is the y value. Remember, our goal is to find an xy value. This is the y value, which is 70 over 11. So what do we need to do? We need to find the x value. We need to pick one of our equations to use. I'm going to pick this 4y equals x equation. We're going to plug in what we just found for y. What did we just find? Yes, I know it's a yucky fraction, but we just found that it is 70 over 11. And this is going to give us our x value. And so when I take 4 times 70 elevenths, you're going to end up with 280 elevenths equals x. Again, a really yucky fraction. This is not one you would want to ever have to graph. With that being said, that 280 divided by 11 for the x value and 70 divided by 11 for the y value, that would be where they would cross. That point, and we can have decimals on a graph, that point would be where these two equations would cross if you graphed them. Again, another reason why the graphing method, it's great because it's a visual. However, when you have decimal answers or really large numbers as answers, you don't want to have to graph those by hand. This is a one solution, meaning we got one answer to this that will make both of those equations true. And that's it for using substitution to solve linear systems of equations.